Hello friends, in this video let us discuss DOL starter for 3-phase induction motor. So I shall proceed with the basics that why starter is used for a induction motor like your DC motor. So it may take time for seeing the whole thing in this video, and I am receiving few comments that sir, the topic which can be taught in 10 minutes you are teaching in 20 minutes. So please see that I am not just time passing before the camera or before you, and I do not like to time pass. It depends on the length of the content and the depth of the subject I am teaching. So you can give time to learning. What I feel is it is worthful to give time to learning rather than some other things. Why do you think you are wasting time? I am not just here to entertain you, you are learning something and I am teaching something. So please do not make such comments that sir, make short videos. I'm always making short videos, and it depends on the subject I am teaching. So let us come to the topic. Here the DOL starter, you may think the topic can be completed in 5 minutes, but I will take some 10 more minutes because I know what the content should be taught so that you can have a whole knowledge about this starter. So the purpose of using the starter in the induction motor is, so in the DC motor, if I compare, the current I is equal to V minus E upon RA, and at the starting the back EMF will be 0 and the armature resistance, that is RA, will be very small. So if a rated voltage is applied, that is 230 upon 0.5, that is I, and this will be very high. This current is very high and it may damage your armature circuit. That is why we go for the starter in the DC motor. Now in the 3-phase induction motor, at the time of starting, that is at the time of starting your slip S is equal to 1. We are fine with it. So if you see the rotor equivalent circuit referred to the stator, so you are having a resistor here, a reactance here, and a mechanical load here. Okay, now this is your R2 prime, this is X2 prime, and this is R2 prime into 1 upon S minus 1. So 1 upon S minus 1, and your S is equal to 1 at the time of starting, and at the time of starting you can also say your induction motor is like a static transformer where the primary is the stator and the rotor is acting as a secondary. So here when you put S is equal to 1, this will become 0. Okay, so the secondary side will act like a short circuited one. So as the secondary circuit acts like a short circuited circuit, the current drawn, that is if I say your I2 prime, will be very high because here it is short circuited. Now as it is acting like a transformer, so this current has to be balanced by your primary current, that is stator current. So in order to balance this secondary short circuit current, your stator will draw also a heavy current, and your modern 3-phase induction motor will draw the starting current from some 5 to 7 times of full load current. So 5 to 7 times it will be higher the starting current than the full load current. Now although in the commutator type motors the electrical stresses is very high, and that is why starter are definitely required for the DC motors or the commutator type motors, but in a 3-phase induction motor the purpose of using the starter is, so although the electrical stresses are very less compared to the commutator type motors, but one thing should be met, that is the voltage, line voltage drops must be within the limits. So that is, if you have a higher starting current, so let me say there is a 3-phase line and you have connected a 3-phase induction motor here, and if there is a higher current received by your 3-phase induction motor, then there will be the higher line voltage drops. And there may be some other equipments connected here also. So there may be some other equipments connected to the same line, and these equipments will get disturbed by the voltage dip occurring across your 3-phase induction motor. So in order to maintain the line voltage within the objectionable limits, so we are going for the starters. So in order not to cause a voltage dip in the line, and it should not disturb the other equipments connected on the line. So if anyone asks you what is the purpose of starter in induction motor, you can tell easily about the DC motors because you have studied very well, but very few people know the purpose of using the starter in the 3-phase induction motor. So this is the purpose, that the voltage dip must be overcome. Now this voltage dip, it can also be overcome by impressing low voltage. So by impressing low voltage across your 3-phase induction motor, you can overcome the higher starting current. So impressing lower voltage, now the lower the voltage, your short circuit current will also be lower in the same proportion. Suppose if you are decreasing the voltage to some k times, then your short circuit current will also decrease in the same proportion, that is k into ISC, where k you can take the transformation ratio or some other ratio, just like in the auto transformer starting or in the primary resistor starting. So if you are decreasing the voltage to some k times of V, then your short circuit current will also decrease some k times of ISC. That is, it will become, the starting current will become k into ISC and the voltage is kV. Now the one serious objection to this lower impressed voltage is, we all know that the torque is proportional to S into V square. Now as you reduce the voltage, the torque will also reduce. So that is why we do not go for this reduced voltage because the torque is also reducing. So it is a serious objection of this reduced voltage starting, where the torque is proportional to V square and the torque is decreasing. Okay, but in the DC motors, your torque will be proportional to I. So as you are decreasing the current, the torque decreases less compared to the torque decrease in the 3-phase induction motor. So this is in the DC motor and this is in the 3-phase induction motor. Okay, we are fine with it. Now let us see the DOL starter for the induction motor. So here the induction motor means it is squirrel cage type induction motor, and I am not talking about the slip ring type of motor, because in a slip ring type of induction motor we are going for the external resistances, and the external resistances will be having their own advantage. Now we are not using external resistance in the cage motor because it is impossible to introduce external resistance in this cage motor, because the cage itself is a short circuited one and you cannot insert some external resistance in this squirrel cage motor. That is why in the squirrel cage motor we are going for the DOL starter, the primary resistor starter, auto transformer starter and the star delta starter. So now coming to the DOL starter, that is, it is also called as the full voltage starting starter. So it is a full voltage starter because, as the name suggests, direct online starter. So this method involves switching your transformer, switching your squirrel cage motor directly to the supply mains. So directly to the supply mains, your induction motor is connected. So that is why it is called as the direct online starter. Now, whether you have to apply normal voltage or reduced voltage, so which voltage you have to apply, it depends on the 4 things. So one thing is, so the voltage which has to be applied across the induction motor depends on 4 things. One is the size and design of the motor, the size and design of the motor, and the second thing is the kind of application. The third one is the location of your motor, and the fourth one is the capacity of the power system or the capacity of the transmission lines to which your induction motor is connected. So based on these 4 things, you decide whether you have to apply normal voltage or rated voltage to your induction motor. Now, although in the DOL starter it doesn't say about the limitation of the size of the motor, so we do not know what is the limitation of the size of the motor that we can use for the DOL starter, because you know in the DOL starter there will be high starting current because there is rated voltage is applied across the 3-phase induction motor, and there will be high starting current. So if you go for a higher rating motor, higher rated squirrel cage type of motor, then there will be higher current drawn by the secondary circuit, and there will be higher line voltage drops. So it is objectionable to go for the higher rating motors, and that is why dual starter is mainly used for the small rated motors, because the starting current can be at least less than the starting current that is for the higher rated motors. So the dual starter is generally used for the squirrel cage motors. So in some books it is written as 1.5 kW, in some books it is written as 5 kW, in some books it is written as 2 kW. So I say the limitation of the size of motor, it depends on the rotor, that is a squirrel cage rotor resistance. It depends on the rotor resistance to which size of the machine you can go for. If it is having higher rotor resistance, then you can go for the higher size also, and you can similarly go for the double cage induction motor, because it is having the higher rotor resistance. Because higher the rotor resistance, it will limit the starting current. So if anyone asks you what is the size of the machine which you can go for the dual starter, then you can say it may be some 1.5K, 5K, 2 kV, but normally it depends on the rotor resistance which you are using, and the voltage to be applied depends on these 4 things. Now, when you use this dual starter, there will be the high rate of increase of temperature, and this high rate of increase of temperature in turn depends on the duration of the starting current, and this duration of starting current, it depends on 3 things again. So the duration of starting current, it depends on the 3 things again, that is one is the excessive load, and other one is the excessive voltage drops in the line, and the other one is the rotor resistance. So upon these 3 factors, the rate of temperature rise and the duration of starting current depends. Now one thing I have to say here, it is the magnitude of your starting current depends on the electrical design of the motor, and it is independent of the mechanical load driven by the motor. Whereas the duration of this starting current, it depends on the acceleration of motor, and this acceleration in turn depends on the nature of load driven. So this is the important thing you have to keep in mind, because in the Viva question they may ask you this thing, the magnitude of the starting current and the duration of the starting current. So let us now move to the DOL starter, that is direct online starter. So this is your DOL starter. This is also called as the push button type DOL starter, where I am having the 3-phase supply. This is R, Y, B, and you can call it as fuse or MCCB. So it is a modular case circuit breaker, and you know the difference between MCB and MCCB, where MCB is a miniature circuit breaker. If I say your MCB is used for the smaller rated currents, that is, if I say it is 100 amperes, then your modular case circuit breaker will be used for some 100 to 1000 amperes. And the difference between MCB and fuse you all know. So fuse contains a metal which melts when it is overheated or when a large current flows, and your MCB, it has a switch mechanism, it gets tripped when there is a high current. So you know the basic differences, I am not going to explain here. So here it is a fuse or MCCB, and here you are having, this is a green color start button, and there will be, you are having a, generally if you see the starter, there will be a red color stop button. So here my marker is drawn without any purpose, that is I am not here to show that the green color is start and the red color is stop. So instead you can make it so it will be in red color. So the stop will be in red color and the start will be in green color, and here you are having a contactor coil. So this is your contactor coil. Okay, these are the main contacts, MMM, and this is the maintaining contact, or you can say the hold on contact, or you can say the auxiliary contact, and here you are having the thermal overload relay. So this is your thermal overload relay, which is generally used for the motor protection. So now these are the parts, and this is your squirrel cage type 3-phase AC motor. So you can say it's simply a AC motor. Now if you see the working of the DOL starter, so initially when you apply the supply, when the RYB is connected, you just give the supply. Now the fuse will be connected, and when the fuse will be connected, there will be the current flowing, and initially the current will pass from like this. So when the start button is pressed, you press the start button. So when you press the start button, it will be closed, and this is, you can also call it as normally open contact. This is normally closed contact. So this start button is held normally open, or you can say it is a momentary contact switch held normally open by a spring, and this is a contact which is normally closed by a spring. So this symbol is which we use in the logic diagrams of the control circuit. So the such symbols like this, like this, like this, these symbols are generally used in the logic diagrams of a control circuit, or you can say it's an electrical schematic diagram. So it is a normally closed by a spring, okay, and these contacts are normally open, and this is also your normally open contact. So when the start button is pressed and when you switch on the supply, so the current will flow from the here, and it will come like this. It will come like this, and this contact will be closed, and it will move and energize your contactor coil, and this contactor coil is connected to the other phase. So generally 2 phases of the line is enough to energize your contactor coil, and when the contactor coil gets energized, these main contacts get closed, this gets attached to the main contacts, and this also closes your maintaining contact or the hold on contact. Now when the main contacts gets closed, then you can see the motor is directly connected to the supply mains. So this is how the motor is directly connected to the supply mains. Now there may be the cases what we see when the main contact, that is the maintaining contact or the auxiliary contact or the hold on contact is closed, there will be a new circuit formed in the DOL starter. Let us see how it is formed. Now the current will flow from here, it will move from here, and it will go to this, and through the stop button the supply will again return back from here. Okay, so earlier the current is flowing from like this. Okay, now the current is flowing because the main contact, that is the maintaining contact, is closed. So the current will flow in the new circuit, that is through stop button, through the relay, and to the contactor coil. So basically this is your control circuit, how we energize the contactor coil. Now okay, we are fine with it. Now if I want to say, there are generally 2 types of protection offered, that is under voltage protection and the overload protection. So if the supply fails or there is a considerable line voltage drops, then the maintaining contacts and the auxiliary contacts gets open. So let us see how it has been, how it gets open. So when the supply fails, this contact gets open, or you can say when the stop button is pressed. Suppose when the supply fails or when there is considerable line voltage drops, we do not need line voltage drops because we do not want to disturb the other equipments connected to the same line, or we can say there should not be the voltage drop, voltage dips in the line. So that is why we say if there is a supply failure or considerable line voltage drops, or if the stop button is pressed, then this contact gets open, and this de-energizes your contactor coil, and when the contactor coil gets de-energized, all the contacts will be moved away, so they will get open. So this is how the under voltage protection can be done, and upon the restoration of the supply, these contacts will be in the same state like in the open circuit, that is they will be moved away, or you can say the contacts won't be closed upon the restoration of the supply. Now though the supply is restored, these contacts will not get closed unless you press your start button. So if the supply is failed, or if there is a considerable voltage drops, or if the stop button is pressed, then upon restoration of the supply, these contacts won't get closed themselves unless you press the start button. So एक बार स्टार्ट बटन दबाना ही पड़ेगा जब सप्लाई फेल्यूर होगा, तभी अपना कॉन्टैक्टर कॉइल एनर्जाइज होके फिर एक कॉन्टैक्ट इस तरह मूव होगा, ओके, तभी एक सर्किट फिर एनर्जाइज होके फिर एसी मोटर सप्लाई के क्रॉस आ जाएगा, ओके. सो दिस इज अंडर वोल्टेज प्रोटेक्शन. नाउ कमिंग टू द, now why we go for the under voltage protection is, suppose if the supply has restored at some time, suppose if the supply is filled at some 5 am and you do not know when the supply will restore. Suppose if the supply is restored at again some 12:30 pm, then the motor will be start working and you do not know where you will be at the 12:30 pm. You may in the industry or you may at outside. So in order to prevent the unexpected starting of the motor, we are going for this under voltage protection. Now in the overload protection, the overload protection is for the control circuit and for the motor. So the overload protection is employs a thermal overload release, which contains a thermal element, and the heat generated in the thermal element will operate the overload relays. So the thermal overload relays are of two types. One is the bimetallic strip, and other one is a solder film type. So the heat generated in the thermal element melts, or you can say it bends. The right thing is the heat generated in the thermal element bends the bimetallic strip, or you can say it melts the film of the solder film type thermal overload relay. So in both of these relays, it depends on the magnitude of the current flowing, because the thermal element is in series with the current flowing to the motor, okay. So the heat generated in the thermal element will depend on the magnitude of current. So bimetallic strip is made up of two different elements whose surface has been welded together, and when the heat is applied to the strip, so if I say there is a bimetallic strip like this and these two are welded here, and if the heat is applied to the strip, it will deflect or curl up or it will bend, and as they are of two different metals, the expansion of one metal is higher than the expansion of other metal, and this causes deflection, or you can say curling up. Now when this bends, the latch mechanism, so this gets opened, the latch mechanism gets released and the motor control circuit opens. When the strip gets deflected. And in the solder film type, so it melts, the heat generated in the thermal element melts the solder film of the solder, and as it melts, the latch arrangement is released. Latch is holding arrangement. So holding arrangement is released and the motor control circuit opens. So this is how the thermal overload relay operates, and here the time of operation of this relays depends on the magnitude of the current flowing in the thermal element. So if you are having higher magnitude of current, then the time of operation is lower, and if you are having a lower magnitude current, then you are having the higher time of operation. And the magnitude of this current depends on the electrical design of the motor, because the magnitude of the starting current depends on the electrical design of the motor, whereas the duration of the starting current depends on the acceleration, and the acceleration of the motor in turn depends on the load driven. So if you are having the higher load, then there will be the higher duration of the starting current. So higher the duration of starting current and higher the magnitude, the relay time operation will be less. So the relays in which the time of operation is inversely proportional to the magnitude of current is known as the inverse time relay. So inverse time relay, it is the time of operation is inversely proportional to the magnitude of current, and such relays are known as the inverse time relays. Basically, inverse time relays are used in the protection of your three-phase squirrel cage type of, or you can say protection of your motor. So this is about the DOL starter. Now coming to the torque and the current relation in the squirrel cage type of induction motor. So we all know that your rotor copper loss. So I have already written here in order not to waste your time. So the rotor copper loss will be given by S into PG, where PG is the air gap power, or you can say the input power to rotor, and the rotor copper loss is nothing but 3I2 square into R2. This will be equal to S into your PG, that is the input power to the rotor, will be given by torque into omega. Okay, torque into omega. Now from here you can see the torque is inversely proportional to slip, and it is directly proportional to I2 square, and the rotor current is again proportional to the stator current, so I2 will be proportional to I1, so I have written torque is proportional to I1 square upon S. Fine. Now your T starting will be, so I have removed this proportionality sign by putting a constant K, so your TST will be equal to K into IST square by S, where at the time of starting your S will be equal to 1. So I have put 1 here, and your T full load will be equal to K into IF square full load current upon the full load slip. Now if I take the ratio, your KK gets cancelled and you are left with IST upon IF square into SF. Now as in the DOL starter, the motor is connected directly across the supply, means your IST will be equal to ISC, because here the voltage applied is a full voltage. So earlier I have said it is a full voltage starting. So as there is a full voltage applied across the stator, the starting current will be equal to ISC. Now in the primary resistor method, in the auto transformer starting method, and in the star delta starting method, where the voltage, if I say the voltage is reduced to some K times of V, then your I starting current will also reduce to some K times of ISC. So there we make your IST as equal to KISC, and if you make IST here K into ISC, then it will be K square into ISC upon IF whole square into SF. So that is how the relation changes in the other methods. So this is all about the DOL starter for induction motor. I hope you understood well. Please subscribe to the channel. Thank you.